Electric cars and solar panels seem like a match made in heaven. Free, clean power as long as the sun shines. A self-reliant solar car that's not dependent on the power grid could recharge sustainably from anywhere you dare to venture, as long as it's not a cloudy day. So, have you ever wondered about bolting solar panels on your Tesla? And why don't all electric cars come equipped with solar panels for a sleek charge-on-the-go solution? In fact, with improving solar technology and clever ground-up engineering, a few self-charging solar cars are just at the point of coming to market. In this video, we'll delve into the practicalities of solar power for vehicles and have a look at some of the early adopters of this emerging technology. In 2017, Elon Musk suggested that Tesla would offer optional solar tiles on the roof of the Model 3, but later retracted the statement, saying that putting solar panels on a car is not that helpful because the actual surface of the car is not that much, and cars are often inside. The least efficient place to put solar is on the car. Did you know that every hour the Earth is hit with more energy from the sun than the entire world consumes in a year? The problem is, the total surface area of the Earth is about 197 million square miles, and the roof of your car is a lot less than that, about 3 to 10 square meters of usable space. It does make a lot more sense to utilize the large surface area of your home with a solar power system like the Tesla solar roof and charge your car from there. The only problem is, you have to be home to use it. A car with integrated solar panels can recharge from any sunny parking lot in the world. And if you happen to be driving in perfect midday conditions, you can even charge on the go, extending the range of your vehicle as you drive. Potentially, the extra incoming power from the solar system could even allow for a smaller, lighter battery system than in a comparable conventional electric car, leading to lower vehicle mass and energy use in driving. To understand if a solar car could really work, we need to find out how much solar energy the surface of a car can capture, and how much range that energy will provide under realistic driving conditions. Solar radiation is often measured in kilowatts per square meter, so let's assume a 1 meter square panel is being hit with about 1 kilowatt of energy in direct sunlight. Unfortunately, nothing in this world is perfectly efficient, especially devices that take raw energy and transform it into useful work. That's just thermodynamics. The most efficient modern silicon solar cells you'd find on a home system only work at best around 20% efficiency. But unlike a house, cars move. This creates unpredictable conditions and can lead to suboptimal solar panel angles. You can technically cover every square inch of the car in panels, but for example, covering the lower door panels isn't going to do you much good, as they won't get much sunlight and the proximity to the road will have them covered in a thick layer of dirt and dust every time you drive. So let's take a sedan the size of a Tesla Model S, almost 5 meters long and 2 meters wide, and put a totally impractical, hypothetical array of solar cells covering the whole plan view rectangular area of 10 square meters. In direct sunlight, it could charge its battery with, at best, 20% of the 10 kilowatts of solar energy hitting it, about 2 kilowatts. With full sun for about 5 hours per day, just as an approximation, that's 10 kilowatt hours of battery charge per day, at best. For comparison, the long-range plus battery option on the Model S is 100 kilowatt hours, so our giant imaginary square solar panel could charge up to 10% of its lithium-ion battery per day. This model has an EPA estimated range of 402 miles or 647 kilometers, so we could be looking at gaining up to 40 miles or 65 kilometers of range with this exceedingly optimistic and frankly unrealistic estimate, potentially a useful extra distance. In a more practical scenario, the solar panels would only partially cover the top surfaces of the vehicle and have a much smaller surface area. Now, no one's saying you'll get 100% of your power from an integrated solar panel system. In the foreseeable future, any solar Tesla would still require the standard battery charging apparatus, but solar could be a useful supplement. Tesla's commitment to solar energy is well known, and the Palo Alto behemoth offers solar roof tiles in addition to the Tesla Powerwall line of energy storage products. According to the 2019 impact report from Tesla, the average life cycle emissions from the Model 3 are less than half those of an equivalent mid-sized ICE car, and if you install a solar power system on your home and charge your EV with that, your carbon footprint can be reduced to almost nothing. This was Elon Musk's idea in 2017, that car roofs are small and inefficiently angled platforms for viable solar installations, and charging from a home solar installation made more sense. You could even charge at night on stored solar and cheaper off-peak electricity. However, Elon might have changed his mind, confirming that the Cybertruck will offer a solar roof option on the truck's bed. On Twitter, Elon said, "Will be an option to add solar power that generates 15 miles per day, possibly more. Would love this to be self-powered. Adding fold-out solar wings would generate 30 to 40 miles per day. Average miles per day in US is 30. In a previous video, we envisioned what a foldable solar array might look like on a Cybertruck, and you may have noticed, we envisioned it as a military Cybertruck and equipped it with some extra goodies. Researchers at NASA's Jet Propulsion Laboratory and Brigham Young University collaborated to construct a prototype of a solar panel array that folds origami style to be used in space. Such a technology might be an interesting concept to explore in the automotive world on Earth, where the greater surface area could increase solar production of stationary vehicles. When it comes down to it, solar vehicles are all about efficiency. It's a matter of energy to weight. A practical solar car would really need to be designed from the ground up with reduced weight and low aerodynamic drag to create a vehicle with more favorable energy density. For as far as electric cars have come in the last decade, the energy density of gasoline is still far greater than lithium-ion batteries. 1 kilogram of gasoline contains about 48 megajoules of energy, and lithium-ion battery packs only contain about 0.3 megajoules of energy per kilogram. Gasoline still has more than 100 times the energy density of the batteries used in most electric cars. This is why planes still use fuel, and why we're not likely to see an electric 787 anytime soon, unless a radical breakthrough in commercially viable battery technology comes into service. Teams gather each year in Australia to race pure solar cars across the continent from Darwin to Adelaide under the scorching desert sun. Back in 2013, a new class of racer was brought into the competition, the cruiser class. Whereas previously, the race was simply about building stripped-down single-seaters. Now designs were welcomed for vehicles which could carry passengers, with additional points being scored for practicality, passenger cars which could perform under normal driving conditions. Consistent winners of this class have been the evolving Stella series from the University of Eindhoven, the team from which Lightyear sprang in 2016. This young startup is one of the most prominent automotive companies pursuing solar-powered vehicles. This is a perfect example of engineering competitions and racing fueling innovation for consumer products, as the lessons learned in the playground of the Australian outback have been incorporated directly into Lightyear 1, the first car offered by the company, which sports 5 square meters of integrated solar cells along its low, sweeping roof and hood. Lightyear 1 reevaluated every component of the car and used lighter materials like aluminum and carbon fiber to build a lighter vehicle with the best aerodynamic coefficient of any car on the market. 4 independently driven in-wheel motors also lower the car's weight and improve powertrain efficiency. In an interview with Automotive EV Magazine, CEO Lex Hoofsloot described the positive feedback loop of weight reduction. By concentrating on efficiency and lightweight, we can use batteries that are about half the size and weight of a conventional EV and half the energy consumption of an EV in the same segment. We have a battery pack that is 2/3 the size that of a Tesla Model S, and we can drive further than the Model S, up to 800 kilometers with good sunlight and a minimum range of 400 kilometers without any solar top-up and with heating, air conditioning all being used and doing high-speed driving. Stop-start and initial acceleration demands power and wastes energy in proportion to mass, typical in urban low-speed situations, whereas the power required for overcoming air resistance increases proportionally to speed cubed, sapping energy at high speeds. How effective the solar charging will be therefore depends largely on how you use the car to balance the energy usage. As Hoofsloot notes, the Lightyear 1 is an electric vehicle capable of 250 miles or 400 kilometers of high energy use driving, even at night, and is expected to achieve a rated range of 450 miles or 725 kilometers, even without its solar panels trickling in their 1.25 kilowatts of extra juice, which the company equates to 10 to 12 kilometers or 6 to 7 miles for each hour of charging, even while driving. This means that, while the car is self-charging, it is primarily a highly capable battery electric vehicle with a small solar capability. Lightyear points out that this solar charge adds up to 10,000 kilometers or 6,200 miles of free motoring per year in the Netherlands, and up to 20,000 kilometers or 12,400 miles in sunnier regions like Australia or California. Lightyear believes that by eliminating the steps between sun and wheel, it should be possible to gain overall efficiency. Lightyear, as Tesla did before them, are starting at the top of the market, coming in at a premium price point of $170,000 for their first full-size luxury car, with future plans to release smaller, more affordable vehicles in the future. Sono Motors, on the other hand, are starting with a more affordable $29,000 compact family car designed for urban use. In designing the Scion prototype, the German startup looked at driving patterns of real-world motorists and found that a typical commute from home to work and back, in Europe or the US, might be up to 16 miles or 25 kilometers. Sono's proudest new technology integrates solar cells into polymer body panels to replace conventional painted metal bodywork. These weigh as little as 4 to 8 kilograms per square meter compared to the 5 to 12 kilograms per square meter for metal or the 10 or 20 kilograms per square meter of flexible or glass-encased solar panels respectively. Importantly, Sono claims to be able to produce these at the same cost as painted metal. Although that includes their initial expense of building and operating a painting production line, a cost which reduces per car panel as more cars are produced. These robust, damage-tolerant plastic body panels have the additional advantage of being capable of mounting to the sides of the vehicle, increasing the solar cell area on a car where glass panels, as used by Lightyear, might be risky. Vertical panels, such as on doors, however, can rarely hope to point directly towards the sun and achieve their maximum potential, and will often be shaded entirely when parked next to walls or other cars. The Sono founders are exploring some other intriguing ideas, including bidirectional charging to allow solar-generated power to be fed into other cars or back into the grid, or even used for grid-connected external renewable energy storage and stabilization. It's not only relative newcomers who are adapting to new technological innovations in solar energy. Toyota has experimented with a demonstration Prius with high-efficiency thin-film triple-junction cells made by Sharp, whose efficiency is claimed to be 34%, compared to that of their commercially available silicon-based solar panel of 22.5%. Energy Solar, a Chinese manufacturer of thin-film panels, have also demonstrated prototype cars with panels that can harvest 8 to 10 kilowatt-hours per day, and supplied such panels to Aston Martin for their GTE racing car. Most solar panels rely on cells made from semiconducting silicon crystals, which convert sunlight to electricity at around 15 to 19%. But new technologies are in the works to create higher efficiency solar cells utilizing new materials. Organic molecules such as polymers can form the light-absorbing layer in a photovoltaic cell and can potentially be semi-transparent, absorbing infrared light and letting visible light pass through, which has intriguing implications for automotive applications such as windows. Organic cells can also be flexible, which can allow them to be fitted onto uneven surfaces more effectively than traditional glass panels. As the future unfolds and more cutting-edge solar technologies come to market, we can see self-charging solar electric vehicles becoming more and more practical as cells get more and more efficient. A future solar technology with efficiencies above 50% would be a game changer and probably make solar cars ubiquitous. Heavy batteries are a limiting factor in the feasibility of solar cars. A breakthrough battery with more favorable energy-to-weight characteristics would revolutionize electric transportation and make solar cars far more realistic. Promising new technologies that utilize materials like graphene, solid polymers, and ceramics are currently in research and development and are poised to create the next generation of powerful batteries with higher energy density, greater service life, faster charging, improved safety, and potentially even lower costs. Most experts agree that we're likely at least a decade out from a fundamental commercial disruption in battery chemistry, but there is a massive amount of scientific and commercial attention on this sector, and a lot at stake, so stay tuned. So, should you mount a solar panel on your Tesla? Well, we wouldn't recommend a homemade conversion with a heavy and delicate, aerodynamically inefficient domestic panel. However, with fresh design of new vehicles whose entire architecture revolves around the solar cells, and a design philosophy of maximum efficiency and lightweight construction, the future is bright, and this technology can be viable. Do you believe in an electric future? If so, please like this video and subscribe to our channel. We showcase cutting-edge sustainable technology. You may be interested in checking out one of these videos next. Thanks for watching and have a great day.